Okay, this video is hitting some of the highlights from Chapter 2 of your Hagen textbook. Specifically, we're going to talk about what Hagen refers to as base units and derived units, and then he goes through this process of looking at a particular engineering formula, for example, and determining whether it's dimensionally consistent. Okay, so these, you can't really underestimate the importance of this. This is something that you need to have become somewhat automatic, all right? You just start working with units and you are familiar with them, and you can easily figure out what to do next whenever you're looking at a formula that requires plugging in quantities that have units associated with them. Okay, so we're going to get started with that, and we're going to look at, first of all, what are base units, okay? So I'm going to scroll down to a table that is given in your book. All right, so he gives tables for the metric system, SI units, for these fundamental base dimensions. Okay, so to help with the discussion of this, he has a different notation for each of the base dimensions. So let's talk about that real quickly. For length, he uses the letter L. For mass, the letter M. For time, the lowercase t. For temperature, it's uppercase T. For current, it's uppercase I. For the amount of a substance, that's in moles, he gives that as N. And luminous intensity, he uses a lowercase I. This is so that we can have a discussion of the types of base dimensions, all right? So under SI units, each of these dimensions has a unit that's associated with it. This is just, what we're going to use for this particular dimension. Now, that's under standard, operational procedures, all right? It's possible that you would start using a different unit or some prefix on that unit. For example, length might be in kilometers. Or if you're working with deep space communication type application, it might be cumbersome to use something like meters, and you would go to astronomical units. Okay, so you can still talk about other dimensions and not have the standard SI unit or the standard English unit for these base dimensions. Okay, so the ones we will use the most will be the meter, the kilogram, second, Kelvin. Sometimes, most of the time we'll use Celsius, but it turns out the degree size is the same for that. We'll get to that when we get to temperature examples in the course. All right. When we get to the electrical unit, we'll talk about amps, and we don't really use a lot with moles and candela. All right. So we have the same concepts that show up in English units. All right, we still have the same fundamental base dimensions. We still have L, we still have M, we still have lowercase t, capital T for temperature, capital I for current, N for moles, and lowercase I for intensity. It's just that we have a different unit for it. Okay, so in the English system, we use the foot as the typical standard unit, but it's not uncommon, if you see an application where someone says the distance is measured in miles, for example, or inches. So these are just the standards that show up in this table. The one that people agree is using, you might think of it as the default units. Okay, now I do want to point out this idea of a slug. It just sounds gross, all right? So I think most people don't use that. I think it's much more common to use pound mass. And one slug is 32.174 pound mass. That is not a coincidence on how that works out. 32.174, if you've had a little bit of physics, you'll recognize that as the English unit gravitational constant. Okay, so when we get to weight and mass in a different video. We'll talk in more detail about that. Okay, so base dimensions. Everything else is derived from these base dimensions. Okay, so you get to a table here, and they talk about different derived dimensions. For example, let's pull one out from the SI units. Okay, force. Okay, force is measured in newtons. That's the standard unit name. But newtons are defined as kilogram times meter divided by second squared. Okay, so you might recognize that. Kilogram is a mass. Okay, meters per second squared is an acceleration. And you've probably heard or seen the formula F equals ma. Okay. All right, so there's the key concept. You have this other quantity. It is not a base dimension, it's a derived quantity. It's force, and it's made up of base units. Okay. All right, so one more example on that. Electric charge. Electric charge is in coulombs, okay, but coulombs is amp seconds, okay, so amps is the amount of current that flows per second, so current is charge per second, okay, so if you undo that, solve the algebra on that, a coulomb is amps times seconds. All right, so a derived quantity. Okay, so at this point, if you turn to example 2.1 in your book, okay, he has an example where he's trying to work out the dimensionality of both sides of an equation. Okay, so the equation in the book is y0 is equal to, y is equal to y naught plus v naught t minus 1/2 g t squared. Okay, so what we know is that y is given to be the height of a projectile at time t. You don't need to know this. Don't let this freak you out. If you don't remember this formula, this is really just an example of dimensional analysis. Okay, so y is given to be the height of a projectile at time t. Okay, and y0 is the initial height. Okay, and then v0 is equal to the velocity at time 0. Okay, t is equal to time, and g is gravitational constant. Okay, so we're going to check the dimensions of these. All right, so when we think of y is a height, so on the left-hand side, that's going to be a length. Okay, and then the initial height, all right, so coming here, initial height, that's also a distance type of measurement, so that would be a length. Okay, and then we have velocity, and what we know about velocity is it's a certain distance per unit time. So that would be L divided by T. If I go miles per hour, it's length divided by time. Okay, so we're just doing this in terms of the base dimensions. So then I multiply by t, okay, and we see that the t's cancel. Okay, and then we have minus 1/2 Next, we need to know something about gravitational constants. Well, a gravitational constant is it's for the metric system, it would be 9.8 meters per second squared. Okay, so let me write that down, 9.8 meters per second squared. If you don't know that, you should know it now, remember it. Okay, meters is in length, okay, and second squared is t squared. And then, of course, time is also t, all right? So what we see here is all these things cancel, and I get L's equaling L's, okay? So I'm not really adding all these things up to make sure that the coefficient out in front is right. I'm just making sure that every part of this, that ends up in an L, this ends up in an L, and this ends up in an L, okay? They can be scaled, multiplied by some constant, but overall the final dimension should be consistent between the left-hand side of an equation and the right-hand side of an equation. Okay, so let's do another example of that, just so that you can follow that. In example 2, he has a drag equation. You don't have to know anything about a drag equation. I didn't before they saw this example. Okay, so FD is 1/2, and then we have this constant CD, all right, times A times rho times U squared. Okay, and so we're going to look at this in terms of a dimensional analysis. Okay, so FD is drag force, and the key word here is force. All right, CD is the drag coefficient. I know this is sounding hard, but really we're just looking at the dimensions of these things. A is going to be the area, the cross-sectional area of the front of the body that's moving through the air. Okay, rho is the air density. Okay, and U is the upstream air velocity. Okay, so you may need to refer to the tables, all right, because these are derived units, all right. Force is a derived unit. Okay, so I go up here and I look at the table and I'm looking for force. Okay, so I see force, and what I'm seeing is kilogram per meter per second squared. I'm sorry, kilogram times meter per second squared. Okay, so kilogram is mass, so I'm going to write that down, cap M. Okay, meter is a length, and then second squared is time. Okay, so I can write that down when I see the force. All right, I would have ml over t squared. All right, so let me drag that down to this example. All right, so that's what I have for force. Okay, so force is here. Okay, and the problem statement is we want to know what are the dimensions of CD. That's the question. All right, now we have area, and I think that we don't have to look that up in the table. That would be a length squared is a cross-sectional area. Okay, air density. All right, so you can look these up in the table, or you can try to figure them out yourself. Okay, so what is density? Okay, isn't it mass per volume? Okay, so if I had mass on the top, what is volume? Volume is like dimension cubed. All right, so if I had, a cube, here's my thought process. that has a volume to it, right? If this was a cube and each had side length L, all right, that would be L cubed as the volume. All right, so it doesn't really matter what shape I drew here. I just know that eventually I get an L cube on the bottom for volume. Okay, so mass per unit volume is density. Okay, so that's what I write down. Next, I have this, I have CD. That's what I'm looking for. I can ignore constants, because constants don't have any dimension to them. Okay, and so area is L squared. And then rho is mass, L cubed, divided by L cubed. All right, and then what do we know for velocity? Velocity is a length per unit time. Okay, all right. All right, and so I'm missing a time. Oh, there's a square on velocity, so this would be squared and squared. Okay, so I noticed, I looked, and the t's weren't matching in the denominator, so that let me know that I had something wrong. So I went up there and I noticed I missed this u squared. All right, so going through this, I can start matching things up. All right, so let me clear the highlighted parts and let's divide things out. So a mass here cancels here. All right, it looks like L squared cancels one of the, two of these, and I just have one L left. All right, which cancels with one of these. All right, and then I have the t's in the bottom, and what do you know? Everything matches up. Okay, so here's an L, here's an L, here's the t squared, here's the t squared, and here's the m, here's the m. So everything canceled, which tells me that CD is dimensionless. I didn't need any dimension component for this drag coefficient, and you'll see that's often the case with engineering terms where we talk about a coefficient. Usually the dimensions on that divide out, and we get something that doesn't have or doesn't carry a dimension to it, just like a constant 1/2 doesn't carry a dimension to it. Okay, so there's two examples of dimensional consistency I'd like you to be able to work through. So what I recommend you do is you do these practice problems from the book so that you can practice this yourself. All right, so these practice problems show up on page 20. All right, so I collect homework, but you really need to do more than just the homework. All right, that's the secret to academic success. And when I give you a hint to do something, go through and work these examples in the book. Okay, when we get to those, I wanted to talk about one of the problems here. Let's skip down to number 4 of the practice problems. Okay, on number 4 of the practice problems, I have m times m minus 3. He's just setting this up as a cosine f L. All right, and he's asking, what are the dimensions of the quantity f? Okay, all right, so here's the thing about that. We only care about f, all right, and f shows up inside the argument of a function, okay? So you've seen from trig, cosine functions, sine functions, we also know about exponential functions. If you are plugging something that has units into a function, then the argument of the function needs to be dimensionless, okay? All the dimensions need to cancel. Okay, so if that's the case, because I have an L here, f needs to be L minus 1. Okay, so that this will cancel and we'll end up with a dimensionless quantity. Okay, All right, so there's the hint on that. I'd like you to work through those practice problems, and hopefully this will help you get a grasp on what we're trying to accomplish with units. Okay, remember the basic idea: base units and derived units. And then because we know what derived units are, we can take a formula like we did with these examples and check the dimensional consistency of that formula.